I'm Aliha Arif, and I'll be presenting a paper today that has been worked upon by a group of scientists from MIT and Brown University. It is titled Learning to Infer Graphics Programs from Hand-Drawn Images. So the outline of my presentation is as follows. We'll talk about the introduction, the motivation behind this research. We'll discuss the roadmap, which is actually the trace hypothesis. We'll discuss stage one of the trace hypothesis, which is obtaining a trace set using a neural network. We'll talk about how it has been trained. We'll see how this idea has been extended to hand drawings. We'll then discuss stage two of this trace hypothesis, which is obtaining a program from the trace set. We'll look into the search algorithm that does it. We'll see what compression factor is. And then finally, we'll talk about the applications of this research. So the motivation behind this research is converting these hand-drawn images, high-dimensional perceptual input, into a trace set. This is the output rendered in LaTeX. And then convert this trace set into a synthesized program, an executable code like this, having for loops, etc. The trace hypothesis is basically the roadmap of this paper, which is basically a liaison between the first part, stage one, which is getting the trace set, and then the program that you get, the code. How does this work? So you have stage one, where you have perceptual input, high-dimensional, noisy, your hand-drawn images. You feed that to a neural network, which then gives you a trace set. Trace set basically are your primitive shape drawing commands, like line, rectangle, line, circle, etc., which give you an overview of your image. What does the image contain? The second stage is feeding this trace set into a program synthesizer, which gives you an executable code having for loops, conditions, etc. So let's talk about stage one of this research, which is getting a trace set. This is brought about using a neural network. The architecture is as follows. We have a CNN boxer, which takes in these two target images. One is the target image. It refers to what we want the CNN to render or give the trace set for. This canvas here refers to what it has already learned. So basically it takes in two inputs, as 256 by 256 crop size, two channels, the output of which is 16 by 16 by 10 feature vector, which is 2560 dimensions long. And you feed this image features to a network of MLPs and STNs. MLPs are your multilayer perceptrons, which then basically give you your next drawing command. These commands are part of your trace sets. How does this work? Okay. So the neural network components are as follows. The CNN box that we saw earlier has these layers. Layer 1, which consists of 20 8 by 8 to 16 by 4 to 4 by 16 convolution or filters, followed by an 8 by 8 pooling with a stride of 4 layer. There's another layer which is 10 8 by 8 convolution filters, and that's why the output of the CNN is 2560 dimensions long, because you have 10 channel or width, right? This is followed by 4 by 4 pooling with a stride of 4 as well. How does this work? So the drawing commands of the trace set are predicted token by token using the multilayer perceptrons and STNs. Token by token basically is a strategy which is being used. Each token is an atomic symbol in the programming language. So the prediction basically is done such that we get a circle, rectangle, line, and then the coordinates like X and Y. So it's not like character by character, it's like one token, second token, third token. Circle command will be predicted, you get the X, then you get the Y coordinate. How is this done? So circle command of the first token is predicted using multinomial logistic regression, using a softmax layer. Usually we know that binomial logistic regression is used for binary classification, right? You get 0 and 1 as output. But since we have 4 outputs for the first token, it can be a circle, it can be a rectangle, it can be a line, it can be a stop sign. So you need multinomial logistic regression, which is given by here, the probability of the first token proportional to your WTF and bias. Okay, so now that you have the first token, we need to predict the coordinates, right? So subsequent tokens are predicted using a differentiable attention mechanism. So now we're talking about coordinates, so we need attention in our model. So this is introduced using STN, spatial transformer networks. Why do we need these? CNNs in general, they lack the ability of being spatially invariant, right? Max pooling layers in CNNs, they do help you in a way that the receptive fields are fixed and local. But we need some mechanism that can allow us to focus on different parts of our image. for which we use STN. STN was developed by Andrew Zisserman's team in 2015, and it's a dynamic mechanism that can allow you to spatially transform your features. We use since then STNs have been used in CNNs to benefit for various different tasks such as image classification, co-localization, and spatial attention. We use them in our network for spatial attention. So how do they work? The spatial transformer mechanism is split into 3 parts. So you have a localization net, you have a grid generator, and then you have a sampler. So what you get as the output from your CNN, the image features, they're represented using U. They're fed into the localization network. The localization network can be a fully connected layer or dense layers. The last layer, however, has to be a regression layer because you want these theta parameters. Theta is your transformation parameters. If in case of affine, they'll be 6D. They'll tell you your rotation, translation, scaling, shear, etc. Transformation parameters, right? And then we have a grid generator and a sampler. Grid generator and a sampler work in the following ways. So you have your source coordinate, which are your input, right? You feed that into your localization network, which gives you the transformation parameters, which then are fed into a grid generator. The grid generator's purpose is to give you a sampling grid so that you know the pixels on which you want to apply the transformation. Once you obtain this, you send both of these to a sampler, which basically multiplies to get both of them and gives you your output pixels, which is given by this equation. You have your source coordinates. You have a theta, which is your transformation matrix, given by this. Since it's a fine transformation, you have 6D dimensional array, and then you take a product and you get the target coordinates, which are your transformed coordinates. So how is this used here? So we observed that the image features that we get are first fed into one MLP, which give you the first token, circle, rectangle, and we use multinomial logistic regression, right, to get this. Though they show 3 MLPs in the implementation, they're using 2 MLPs. One MLP is for the first token. The other has, for the coordinates, we use just one set of STN and MLPs, multi-layer perceptrons, right? And they use regression to give you your coordinates, where the object is. So once you have the CNN network going, the output can be written in this form. The probability distribution, we can observe this in terms of next drawing command. The drawing command is your rectangle circle statement. So this basically represents that. Here, f theta represents the output of your neural network, which takes in your input image and the rendered image that you are obtaining trace by trace. And it then and A theta here represents the attention mechanism. So you apply this on the output of your neural network, right? And then you predict the next token, which is given by TK, given this previous information. Here also you see tokens that are predicted given your original image and what it is already rendered, the network what is already understood. The same distribution can be factorized over traces. Here we see that you have your trace set given the original image. Tn, the subscript Tn here refers to each command in the trace set, like T1, T2 are the commands in the trace set. So if initially n is like 1, you see you have an original image and the rendered trace set or the rendered image is nothing, it's T0. And then you produce the first command. The last command has to be a stop command, and that defines that the trace set is now finished and it's now representing the original image. This is taken from this part, the P theta token given IT. So now, how do we train this neural network? See, if the network predicts something incorrectly and we try to de-render, we go from the output towards the input. If it is already given a wrong trace set, we'll not be able to get the original image back properly, right? So to make the network more robust, an SMC technique is employed. SMC is sequential Monte Carlo sampling technique, which uses pixel-wise distance as surrogate for a likelihood function. So what it does is, in general, this is a concept we should know that in computer graphics, SMC technique is used. Okay, they do it to make the network robust. Here, how does it help? So when you get the output from your neural network and you sample the random pixels, and then you apply pixel-wise distance as surrogate, so the chances of not overfitting the model, they increase. At the same time, when repeated sampling of the same pixel would actually mean that the average of the samples will converge to the ground truth more quickly and more fast. So that's how the network becomes robust and it trains more efficiently. We compare the results when we apply SMC and when it's not there in this graph. So here, if you look at the x-axis, it says objects. The objects refer to your trace set, the commands in the trace set, because each line is telling you about your image, right? It has circle, rectangle, so these are your objects. The y-axis here shows you the average program edit distance. Edit distance is given by the size of the symmetric difference between the ground truth trace set and the set that has been produced by the model, the neural network. So what do we observe? That the baseline LSTM does not really work well when they use it. This is the baseline, the yellow line that they're using. Even if it has more objects, less objects, it doesn't matter. There is always this error that we get between the ground truth and the trace set produced by the model. When we use SMC again, only SMC does not really help, of course, because there's no network. And then when you talk about the neural network alone without sampling, this is the blue graph that we get. It works well when there are less than 12 objects, but then as soon as the number of objects or commands in the trace set increase, it starts going higher. But in the red line, this shows this SMC plus the neural network model that we have just talked about. Here, even if the number of objects or commands in the trace set are less than or more than 12, the edit distance comes out to be 0, which is pretty nice, which is pretty good. Okay, now we'll talk about generalization to hand drawings, and that's the main idea, using hand drawings to get a trace set. So actual hand drawings are never used. Rather, a noise is actually introduced in the rendered training images, and then that is used to train the network. How is that done? So in order to produce a set which mimics hand drawings, they rescale the image intensity by factor, chosen from 0.5 to 1.5 in a training target set. They translate the image by plus minus 3 pixels, and then they render this lattice version using pencil drawn style to mimic hand drawings as much as possible. So we know that the hand drawings will never, the network's output is never going to match the hand drawings, right? Because they have noise and the output of the model will always have a difference. And pixel-wise distance likelihood function will never work perfectly. So we come up with another likelihood function, L learned, which is given by this equation. Here you have T1 and T2. These are your two trace sets. T1 is the rendered output with noise, the one that mimics hand drawings, and T2 is just the rendered output. So what you want now is to make the network predict two scalars, T1 minus T2 and T2 minus T1. This basically helps it understand hand drawings as well. Okay. Once this all is done, we are going to evaluate this neural network to see how well it works. For evaluation, 100 hand-drawn images are now used. Now when I say hand-drawn here, I'm not talking about the rendered one with noise, I'm actually talking about actual hand-drawn images. This is for testing, right? So these are made on graph paper, snapped to a 16 by 16 grid. This is the chart that they used to show how well the network works. So percentage of drawings tell you the number of drawings that have been used to test this network. And IOU here, intersection over union, is basically an intersection over union between ground truth and the predicted trace set by the network. And this IOU is used to measure systems accuracy at recovering the trace sets, So if you look at this diagram, you see different colored lines. So these basically represent your different networks. When there is no guide, you see this black line that comes up. The blue represents the line when there is no distance-wise pixel used as a likelihood function. The yellow is when there is no sampling scheme done, green when there is no attention mechanism used, and the red is when you have the full model using SMC, your guide, your attention, your SMC. Attention. Yeah. So this is what, and we see for every line, every color, there are 3 lines, right? So the solid line tells you the top 1 accuracy. This dash one is for top 5, and the dot is for top 100. So what do we observe when you use the full model? When the intersection over union is 1, that is the ground truth and the model's output are completely overlapped, we see 63% of the drawings basically have a top 1 accuracy. And when we look at the top 5 accuracy, we see around 70% have top 5 accuracy when you're using the full model. So the network works pretty well. Now we'll move on to stage 2 of the trace hypothesis and this research, which is obtaining a program from your trace set that we just obtained, right? So the program that the authors use to write their code is in DSL, domain-specific language, and they use frame meta as the framework. And this is what it's going to look like. It will have statements, you have variables, and etc. So in order to find the program that best describes your trace set, they define a cost function. So when they say cost, they're looking for a program that is most concise, most small, and has the minimum cost. So how do they define cost? Cost is computed in the following way. Programs incur a cost of 1 for each command in the trace set, like there's a primitive drawing, action, loop, reflection, etc. There's a cost of 1. And they will incur a cost of 1 by 3 for each unique coefficient. These are linear transformation. So the idea is to use or to find or look for a program that is concise, smallest, so that has less number of loops, reflection, etc. to give you minimum cost. At the same time has more coefficients, right? So that overall the program has less cost. In order to look for such a program, they come up with a policy which is based on bias optimality search algorithm. Our search algorithm is n-bias optimal with respect to any distribution, p-bias, if it is guaranteed to find a solution in sigma. Sigma here represents your program space for all possible combinations, after searching for at least n times t sigma p-bias sigma. T sigma here is the time it takes to look in the program space and tell you if it has a solution for the trace set or not. Intuitively, we can say that it will take p-bias by n times to look for a program. We make use of one bias optimal search algorithm, which means p-bias by 1, we're looking at the whole program space. And the idea is to search for all possible combinations but focus on areas that are more promising. Our policy is given by this notation, pi theta sigma given t. So you have your trace set, and sigma here is the best program you can come up with for that corresponding trace set. We need to have a loss to train the search policy, right? So the loss the authors have come up with is given as follows. Here you see D, which is the training corpus, that is the set of minimum cost programs for few trace sets that can be used for training. Theta here denotes the parameters of the search policy. The equation basically says you need to look for a program. You need to basically minimize the time searching for the best program given the search policy. Lambda is just a scalar and theta are your parameters. So you're looking for the time, so you're looking basically for the search policy such that in the fastest possible time it's going to give you the most suitable program for your trace set. This, our search policy is represented, or basically it's a bilinear model, and it's proportional to exponent of these two vectors, the scalar product of these two vectors. 5 parameters here basically is a vector that denotes a one-hot encoding of the parameter settings of sigma, and it's 24 dimensions long. When you say parameter settings, we're talking about the parameters of our program. So these are the parameters that this policy questions when it is searching in the program space. So it asks if it has loops, does it have reflex, does it have incrementals, maximum depth, etc. And you see the output is like you have two combinations, 2 and 2 and so forth. So when you multiply, you get a 24-dimension long vector. So these parameters are questioned, and then it comes up with the program that has the minimum cost and explains your trace set. Phi trace here refers to features of your trace set. So this search policy that the authors propose, they compare it with state-of-the-art existing sketch tool, program synthesizer, and Oracle, which is like a human output. So of course that is the one they cannot beat. It's 6 seconds, the median for which, so this represents the time it takes on average to look for your program, right? So when they compare it with Sketch takes around 274 seconds to give you a program, the best program for your trace set. Whereas their learned policy is just taking 28 seconds to give you a program for your trace set, which is pretty nice. Compression, okay. So this basically is just a comparison of how the program that you obtain is better and how well it explains your image. So if we write a trace set for the image, it takes around 21 lines to describe this Ising model, which is a still lattice structure, right? You have circle, circle, line, circle, and so on to tell you the objects that you have. But if you write the same thing in a program, you just have 6 lines to represent the same structure. 1, 2, 3, 4, 5, 6. So you actually compress your image or your code by a factor of 3.5. There's another example. Here you see there are like 13 lines in the trace set which are just describing this image. But when you use a code, you just have, again, 6 lines, and you compress this code by 2.2, by a factor of 2.2. So lastly, we talk about the applications of this research. The first application is correcting, when you get a program, you synthesize a program, the errors that have been made by the neural network can be corrected using prior probability. You have this hand drawing, which is your input. You feed that to your neural network, and you obtain a trace set. The output, if you render it in LaTeX, it appears something like this. So it reads the drawing incorrectly. It adds an arrow here. At the same time, adds a line here, which is not in the original image. But when you actually synthesize a program, you see it gives you an image which is exact or same as the hand drawing or as the input. Why? Because program synthesizer in general supports or favors aligned objects. Because there will be a loop which is going to just draw this pattern 3 times. So exact same pattern is drawn 3 times using a for loop and a program, whereas here when it was rendering, it gave you this error. Another application is you can model similarity between drawings by looking at the program code. For example here, if we talk in terms of the program space, so we'll see that this image and this image will have same number of for loops. One for loop for drawing the 5 circles, one for drawing the 5 rectangles. So in terms of how close they are, you can say that these 2 images are close just by looking at the code. When you talk about close in image space, we'll use pixel-wise distance or a similar metric to compare them, and that will also tell us that these 2 figures are pretty close to each other. These 2 figures, however, if you talk about the code that will be generated, will be pretty much different. And just by looking at the code, you can say these figures are not close or not similar looking. This is another example where by looking at them, you can say, by looking at the code, you can say that they are close in program space, but visually, in image space, they're not similar. And lastly, these are the examples of programs which are dissimilar completely, even in the program space and even in the image space. Another application is extrapolating figures. You have this hand-drawn image, original image, right? And you get a code for it. Program synthesizer does that for you. In just that program that you get, you can apply more iterations and come up with this structure just by modifying the for loop a little. So you can extrapolate your original image just by using the code. In another example, we see there are 3 squares, right? If we just again increase the iterations, we'll end up with 4 squares. So you can come up, you can extrapolate figures, you can make more figures, more dense figures using the source code. And yeah, that's it. Thank you.
Okay, good.